Hello, everyone. Welcome to Coffee with Caleffi. Today, we are talking about aligning to design. So, we're going to do a deep dive on DHW recirculation topics with Kevin Freidt. He is our Director of Product Management and Technical Services. We'll give his bio a little bit later here. A couple housekeeping things. If you're having issues with audio, probably just log out and log back in is usually the quickest fix. If you want a copy of the presentation, when you exit or when the webinar finishes, there'll be a little survey and you can click yes there. And then we'll also put this up on YouTube later today if you want to come back and listen to the rest of it or pass it along to a colleague. Certificate of attendance, if this is useful for you and your jurisdiction, just by registering, we have the information to fill out the form, and then we'll send this to you after the webinar has concluded, so you can submit that wherever it's useful. And then Hydronics 35 is available online now, and the hard copies have been sent. So if you're missing that, I'll put a link in the chat for where you can register for Hydronics. And then we're working on number 36 currently. Next month, we've got kind of backed by popular demand. We spend a lot of time talking about this IAPMO water demand calculator. So we're going to have three of the experts from IAPMO come back and give us an update for what the latest information they have in this water demand calculator, what applications it fits for, and kind of hear it right from the source. This has been a really big topic and a really useful tool for us, and something we look to hear more about next month. And this month we have Kevin Freidt. So again, he's our Director of Product Management and Technical Services. He's also an expert in the industry and is on a bunch of different working groups with ASPE and IAPMO for standards and kind of code development project groups. So I'm going to turn it over to Kevin, and I'll keep an eye on the questions and put links into the chat. So thanks, Kevin.
Thanks, Max. Thanks everybody for being here today. Let's go ahead and get right into it. So this is a we have a new practice here where we're mentioning charitable contributions every month. This is a new thing that you'll see with the Coffee with Caleffi. And this particular one, I am actually on the board of directors of Take It to Heart, and it is a wonderful nonprofit. And all the money we gather and raise goes to the Herma Heart Institute at Children's Wisconsin here in Milwaukee. And maybe not something you know, but CHD is the most common type of birth defect. So it's a very important cause, and you can see that it affects a lot of babies worldwide. There's the Take It to Heart for Kids.org. If you would like to, I'm sure that your contribution would be much appreciated. Thanks. All right, let's get into the agenda. So why recirculate? We'll start at the beginning. Why do we even do that? Turns out that's actually a human factor, and we'll get into that a little bit. We'll talk about the circulators, being the heart of the system, how to size those, what to do, what not to do. We'll talk about piping design best practices. So all you designers and engineers out there, you can critique my approach there. And we'll talk about velocity. We'll mention mixing valves, how they fit into the big picture of recirculation. We will mention anti-scald valves. They're part of the system as well. Talk about whether or not we need them. Balancing is a big part of the recirculation system, a very, very important part, and probably one of the parts that actually generates the most questions for our technical support group. And we did get a few questions come in mentioning, can we talk about high-rise buildings? What does recirculation look like in high-rise? And I've got a couple of slides on that too at the end. And we should have plenty of time for Q&A. By the way, if you have a question or a comment, enter them in the little, you'll see the little comment box or question box, the chat box up there. Go ahead and enter your questions as we go through. And if Max sees a good one, or if Bob Rohr sees one, we can chime in and talk about it anytime. All right, I mentioned that recirculation is a human factor. Well, the number one most important reason we even do this is because of wait time. When we need hot water, we want it right away. We don't want to wait. So that's the human factor I mentioned. This chart is really helpful. Gary Klein, one of the gurus in the industry, sent that over to me. And when we talk about wait time, what does it mean to us as individuals? If you are using a lavatory sink in an airport, you don't want to wait more than a couple of seconds for warm water. Maybe if you're going to take a 5-minute shower, 15 or 20 seconds is acceptable to you. So there's no hard and fast rule, but we do have some guidelines here. So when we're talking about time, that's a good reference. Now, I want to talk about this diagram a little bit. So I'll be using this kind of schematic throughout the presentation, and it's a very basic schematic. It's not meant to show everything. For example, you won't see expansion tanks or pressure reducing valves or backflow preventers. It's a fundamental schematic just to illustrate the principles. So in my slides, I have a storage water heater. I should say that this could actually be a tankless water heater. It could be a heat pump water heater. The schematics don't really call that out. So it's just a representation of a heat source. So when we look at this diagram, we have our hot water supply coming here in the hot water trunk. That trunk goes out, and then in this particular single loop recirc schematic, it just shows a limited number of lavatories and showers. We'll get into some multi-branch recirc loops here in a minute. So then that recirculated water comes back via the recirculation circulator and then back to the hot water source. So in general, I just want you to understand what these schematics are trying to tell us here. Now this one, we show ASSE 1070 and ASSE 1016 scald protection valves at each point of use. So that may or may not be required, but in this particular schematic, we do show them. So the wasted water, when we talk about wasted water, that's number 2, by the way. Number 1 is wait time. Nobody wants to wait for hot water. Number 2 consideration is the wasted hot water that we're dumping down the drain, because we've heated this water, we've spent money on it, and we don't want to just dump it down the drain. So when we talk about wasted water in a system like this, where we have a recirc loop, what we're actually wasting when we open a fixture is only the water in between the takeoff on the trunk out to the fixture, so it's a small amount. If we didn't have a recirc system here, wasted water would be anywhere from the fixture all the way back to the tank. So that can be a lot of water, and you can see this specification here also from Gary Klein, that the average home wastes over 3,600 gallons of heated water per year. And if we were heating from 50 degrees to 120 degrees, and if the cost of that electricity was 15 cents per kilowatt, we'd be spending almost $100 a year in electricity. So that's a significant amount of money. So number 1, the wait time. Number 2, dumping wasted water down the drain. And then number 3, paying for all that. Waste equals money. There we go. Another point in that first sentence is to deliver safe hot water to all the fixtures. When we're talking about safety, the number 1 point to talk about is temperature. So again, this schematic shows anti-scald valves or point of use valves at every fixture. And if we're going to run this recirculation loop at any temperature above 120, we need to have anti-scald protection. And you can see in this graph here on the left that 120 degrees, if you come straight across, it's pretty safe. It's considered safe because most people can get out of the way of that 120 degree water, and it won't scald you for a few minutes. So generally that's considered safe. But if we're going to run temperatures higher than that, 130 or 140, that's when we have to have anti-scald valves. Now, if we were running this tank at 120 and sending out 120 degree water through the building, which would be more like a residential application, we wouldn't need those anti-scald valves. But now we're getting into some temperatures that are less than 120, and that can be problematic. I'll show you why. I like this chart on the right because it shows the relationship between the ideal growth range of Legionella bacteria, and temperatures. So now this is a laboratory condition. So these numbers are, theoretical, but below 122, you can see in this green range that bacteria can grow. You can see the ideal range is here between 95 and 115. So when we're talking about recirculated hot water, if we let that water get into this range and sit there for a while, then we risk the potential for bacteria to proliferate. And really, that's more of a concern in commercial applications. If you think about your residential application, your house or my house, for example, we go through a lot of hot water. So all of the water in most homes is refreshed, a few times per day, unless it's a vacation home, right? If you're away from home for a period of time, then that water has a chance to sit there. But in normal operation, we don't worry too much about Legionella growth in residential applications. But in commercial applications, that's a different story. So the UPC and IPC codes, for example, specify a minimum of 140 Fahrenheit for your storage temperatures. Why do they do that? Because of this table on the right, right? You want to, if you store at 140, you will not have Legionella growth in the tank. And theoretically, then we don't want anywhere in that recirc loop to drop below 122 if you're using this chart here. Another thing we want to look at as far as safety is maintaining a minimum velocity in the piping. I'm going to get into that in a few slides. That is actually another factor involved in safety when we're talking about hot water safety. Here's a slightly different graph, similar but different. Now this one is a multi-loop domestic recirc loop, and you can see that the hot water trunk is the same, but now we have, I'll call these risers or secondary circuits or takeoffs, whatever term you might use where you work. But in terms of designing a system like this, the designers want to minimize fixture runouts. So a fixture runout is anywhere from the hot water source to the fixture. Now in this case, where in this schematic here, this runout, the hot water source is this riser hot water pipe right here. So the runout is this piece right here. We want to minimize that, and some codes actually specify 50 feet, for example. The IPC specifies 50 feet. I know that local codes are more stringent. So if you can type in the chat, or if you have a question, tell me what this length is where in the jurisdiction where you live. We'd be interested to find out. So as a designer, you want to minimize those. Why? Because anytime that fixture is not used, you've trapped old water. The water is trapped in that runout, and it can get old and potentially contain bacteria. Also, we don't want to design for dead legs. Never design or install a dead leg planning for future expansion. Those are just problems. Don't ever do that. That can be a source for bacteria. And stagnation is one of the big factors for biofilm growth. Let's talk about velocity. When you size your piping, you want to have the right velocity, not too high, not too low. Let's talk about that a little bit. We know that excessive velocity will cause noise, right? I think you can, even in your own home, when you have high velocity going through a pipe, you can hear it. And what we can't see is potential erosion. And there are references, like the Copper Development Association has references that says for hot water, 4 to 5 feet per second, 5 to 8 feet per second for cold water. And when you are above 140, lower that velocity to 2 to 3 feet per second. So velocity is a very important consideration in designing and sizing your piping. And PEX, I saw a few references that say 2 feet per second for PEX. So, and I think Max knows about that too. And that's what I found. Haven't seen any other numbers for PEX piping, but even lower. So an oversized recirculation pump will also waste electricity. It'll waste energy. So we're going to talk about sizing the pump here in a minute, but that's also, if your pump is too big, you're going to have too much velocity and cause the problems we just talked about.
Hey
On
Kevin,
the other, yeah,
I've got a couple answers that people have typed in about the run out length. So I've got a 25 foot. I've got an international energy code requirement, which ends up being about 6 feet, and then a run out should be based on the pipe diameter, pipe length, and flow rate. So a lot of different answers. I know that in some jurisdictions it can be 50, but it seems like that has come down, which is good. And again, from the like recirculated loop, not from the physical water heater, I guess, being one other note here.
yeah, I see a lot of different. In fact, I took a tech call this morning and it was about the size of the pipe. Like if you downsize to a 3/8 inch for your run out, you can have a longer run out. And I guess that has to do with the volume of water that's in that run out, right? The smaller pipe will have less water in it. So you'll get the hot water faster. Good. All right, now what about velocities that are too slow, too low? Another person in our industry who's an expert reference is Andrew Jock, and he sent me this information about maintaining adequate velocity to perform some debris and biofilm control. So you want enough velocity to keep that water moving. If it's going too slow and you have laminar flow, then you can have thick debris and biofilm accumulation. And that causes something called microbiological influenced corrosion, or MIC, on the surface, and it's actually worse on the bottom. So really low velocity isn't good either. Okay, now this is a controversial subject. Circulators. You can see in this bullet here that according to this ASPE CEU document, we should run the circulator all the time. And you can see that quote there that OSHA and ASHRAE 188 mention it. There's the OSHA reference saying that the circulator should be excluded from energy conservation measures in favor of keeping the water moving. On the other hand, you have some other references. This one I found says that there should be demand controls on the recirculator. And we know that, excuse me, in some areas like California, the energy codes say you have to put an aquastat or some kind of a time clock on them. So there's two camps. I believe that we should just run these all the time because today's smart pumps are very, very, very efficient. It's really the energy that a smart pump will consume is almost negligible in terms of the total energy that you're using to heat this water. So that's my opinion. Probably some people disagree with that, but that's where I'm at. Okay, and sizing the circulator. Let's talk about sizing the circulator. There's two steps. The first step in figuring out which circulator you need is to calculate your flow rate. And the way we do that, let me go ahead and go down here. To calculate the flow rate, you use this equation here, GPM equals BTUs per hour over 500 times delta T. So what you do is you start at the heat source. So if you can see my pointer here. So for this first riser, we're going to start right here and we're going to go up, across, and up to the end of this. And we're going to use that section of piping to calculate a GPM based on the delta T and then the BTU per hour per foot of heat loss in that one run of the piping system. So you will come up with a GPM for this piece here. The second piece is right from here. So at the bottom of that first riser, over and up, the second piece is this section of piping. So you would calculate the GPM you needed for that section, and you'd do the same for this third section. So you would start right here, look at your heat losses for this piece, and you'd come up with a third GPM, and then you add all those together because this trunk has to deliver this GPM, and this GPM. And we're not going to get into all the details here because it's all drawn out in Caleffi Hydronics issue number 21 if you want to look at the math and the theory behind all that. Just wanted to illustrate that step one is determine the flow rate for your circulator, and that's the equation you use. Number two, how much pump head does the circulator have to have? In this case, you want to try and figure out the longest run in the system. So in this simple schematic here, I just drew the lines, probably this longest run here, all the way out, all the way back to the circulator and back to the tank. So that's where you need to use your standard piping loss calculations with the runs and the elbows and the isolation valves and the balancing valves too. You need to account for everything that causes head loss in that circuit. The balancing valves are part of that circuit. So if you're using manual balancing valves, you have to use the CV of that valve, depending on which one you use. If it's a manual valve, you will find in the manufacturer's data the CV of the valve, and that's the CV you use to calculate the pressure drop across the valve at the GPM that you just determined, right? So you have to account for that. If you're using automatic valves or constant GPM valves, some people call those dynamic valves or pressure independent valves. Each of those, depending on who makes them, they have a minimum DP requirement. Ours have a minimum DP of 2 PSI. So you can actually, as a rule of thumb, you can use 5 feet of head loss across an automatic balancing valve like the type that we make. So it's a question because they don't really have a CV. These type of pressure independent valves don't have a CV, and we get the question, well, how do I figure out what the head loss is across those? Just use 5 feet of head loss for those. The new thermal balancing valves are a little bit different. You have to look at the manufacturer's literature and look for the design CV. You don't use the maximum CV because they almost never operate at maximum or full open. Thermostatic balancing valves they modulate from almost closed to about 10 degrees Fahrenheit when they're open. So that's the range they work in. And most manufacturers have a design CV. That's the CV you'll use to determine the head loss for those. So when you do that, okay, let's just say, for example, that you came up with 4 GPM for that circuit and a total head loss of 10 feet. Then you use a pump curve like this, and you have to find a pump where your flow and your head are in the working range of that circulator. And I don't know if Bob or if Max, if you want to say anything about this. I'm not a circulator expert, but this is what you want. You want to be able to have that work in the range that you've calculated.
Yeah, I'll just add that this technology seems like it's getting better every day, and the circulator manufacturers have a lot more programming choices too. One of the things to just double check is if these recirc pumps are operating on some sort of temperature-based setting. We'd want to make sure that doesn't conflict with what the temperature-based thermal balancing valves are trying to do, because you can have kind of two different hands on the steering wheel there. So if you're using a manual or an automatic balancing valve, then temperature-based setting might be the right one. But you maybe want to use a pressure setting if you're using thermal balancing valves like Kevin's showing on the slide here.
Yep, good lead in. So smart circulators are the way to go. We certainly believe so because they respond to system changes like Max just said. So what I like to think about is if you had a smart circulator and you set it to constant differential pressure mode and you're using thermostatic balancing valves, to me that's kind of a perfect marriage, to build on what Max just said. If the thermostatic balancing valves are opening and closing, they modulate, right? So they're the only kind of balancing valves that actually change the GPM as the system dynamically balances. So the thermostatic balancing valves are controlling temperature, and as they do their job, then a smart pump set to constant differential pressure mode will ramp up and ramp down to maintain the required head in the system to get the right flow. So they go together very well. Let's talk about master mixing valves. In general, a mixing valve will extend the capacity of a hot water tank. So that's why you would put that on the hot water tank at your house, to extend your 40-gallon tank, maybe extend that up to effectively a 50 or 60-gallon tank by tempering the water that goes out to your fixtures. Now, mixing valves, ASSE 1017 or point of distribution mixing valves like we show here, have to be piped correctly when you have a recirc system. So let's talk about that a little bit. Here's just a schematic of a thermostatic mixing valve, and then the circulator is bringing the water back from the system. And you'll notice that there's a check valve here, and let's ignore the return valve and bridge valve just for a minute. That water has to come back to tee into the cold inlet of the thermostatic mixing valve, and that water has to also go back to the tank. So if you don't have a recirc connection on your tank, you can tie that in right here. Okay, and you need to have a check valve down here to prevent that recirc water from going this way. So this is very important that these valves get piped this way. If you have a tank that has a recirculation connection, I would say that's going to be a commercial tank, right? I don't know of any residential tanks that have a connection. But what you do is you come back, here's that same recirculation circulator, and the water either goes here, which is the same place, right? It's the cold inlet of the mixing valve, and then you tee off and then you go to your tank. So the piping, whether it's a little bit different, whether you have a tank with or without a recirc connection. This won't work, okay? If you have a recirc connection that comes back and just tees in right here, that's not going to work. Why? If this valve closes the cold inlet port, the recirculation circulator is going to deadhead because the water can't go in here, it can't go into the mixing valve, and it's not going to go backwards through this check valve. So that's one main reason. Now let's think about this. If this circulator is running and there's no water being drawn at the fixtures, there's no cold water coming into the system. So even if this valve didn't close, if we just circulated this water like this, around and around and around here, eventually it's going to give up heat to the space, and that loop is going to cool off. That's called droop, recirculation droop. And we're not going to have any hot water coming into the thermostatic mixing valve. Why? Because there's no cold water going into the tank. If you don't have any cold water going into the tank, you won't have any hot water coming out of it. Okay, so that's one condition called droop. So the first person in the morning that opens a tap is going to get water that's colder than they expect. Another thing to talk about is something called temperature creep. Let's talk about that a little bit. If you have a thermostatic mixing valve that does not close this hot inlet port 100%, that can be a problem. Not always, but it can be. Let me talk about that. So again, at night when there's no fixture usage, there's no fresh water coming into the system, right? The only time fresh water comes into the system is when you open a fixture. Otherwise, it's a closed loop system. You can think of it that way. So this recirculation water is coming back. It's going into the cold inlet of the valve. It's also going over here into the tank. Now, if this hot port on the inlet of the thermostatic mixing valve doesn't close tight, you're going to have a little bit of water going into the tank, out here, and going back and coming into the mixing valve. So it can happen that if there's more hot water flow, if there's more BTUs leaking through this valve than you're giving up to the atmosphere in your system out here, the whole loop will heat up. Okay, the whole loop will heat up, and that's called temperature creep. So too much flow through the tank into the valve and out will eventually cause creep. And in the morning, when someone opens up a fixture, they're going to get a blast of hot water. So how do we do that? What do we do to fix that? What we can do is add these two little balancing valves here. Actually, this one you don't actually need. It's in the schematic, but say that's not there. You need this bridge valve. This is the one that's really important. And it has to be a fine adjustable valve that you can tweak. And this takes some time, but you can do it. You close it almost all the way closed so that it allows very little water into the tank, just enough BTUs coming out of the tank to equal, ideally, to equal the heat loss in the piping to atmosphere out here. So if you can get that balanced just right, then you won't get temperature creep. But this valve is just barely cracked open, and that takes a little bit of work, a little bit of practice, but it can be done. On the other hand, if your master mixing valve can close off 100% tight on this hot inlet, like a digital master mixing valve that's a ball valve that can close off tight, you don't have to worry about any of this. Okay, this all goes away. Temperature creep will not happen because the valve can close off completely. A problem we hear about related to master mixing valves in our technical support center here is, the valve used to work great. It was fine for 6 months or a year, and now we have inconsistent hot water supply temperature. Usually, what we find is this: bad water conditions, poor water quality can cause a valve to look like this on the inside when you take it out. It can get scaled up, it'll get stuck, or it'll be choppy. It'll open a little bit or not open a little bit, and basically it's getting locked up. The good news is you can clean these, okay? In a residential application, you can just take out the body, and Bob's the expert on this. You can put those in a bucket of descaler or anti-scale fluid, and you can rinse them out and clean them and put them back in service. You want to chip in at all, Bob, or does that pretty much cover it?
Yeah, no, that's exactly it. And how often you have to do that really depends on a couple things. Number one, how hard your water is. The more minerals or deposits in your water, the more often you have to do it. How much water you use. If you have a family that uses showers a lot of hot water, the more water you put through it, the more minerals you're putting through it. And also how hot the water is. The hotter you run your domestic hot water in your tank, the more the minerals precipitate out of it. So if you're going to elevate your tank temperature to 140, like we've been talking about, expect to get more minerals. So, if you've got a building where this is critical, you might have a backup one ready to go and just switch out the union nuts and then take the one that's plugged up and just soak it overnight in a descaler, and then you always have a quick couple-minute fix for that instead of having to take it out, have the building shut off for a period of time until you can service it. But yeah, it's really hard to make this go away. I mean, we want some minerals in our water. That's what makes it taste good. If you filter it down to deionized water, that wouldn't be very good water to be in your piping or in your body. So you're going to have to deal with scaling, regardless of the brand or the type of mixing valve. It's like rust; it never sleeps.
Right, right. And if you get that call, if someone said, "Well, it used to be great, and now it's not," I'd bet you a cup of coffee it's scaled up, and it can be cleaned. All right. Oh, I missed a point here. Some digital mixing valves have a feature called anti-clog or something like that. What the digital mixing valve will do is every night it'll fully open and fully close. And what that feature is for is to kind of clean off any buildup or scale that's on the seat of the valve. And the Caleffi valve does that, and that makes it for a pretty good feature. If someone has really hard water and they know that scaling is a problem and they have to rebuild their master mixing valves all the time, that can really help with maintenance costs. All right, another big thing that we hear about in our technical support center is hunting. The valve is hunting. It's cold, it's hot, it's cold, it's hot. the valve has to be the right size. The master mixing valve cannot be oversized. If you put a valve in that's too big, then it's trying to control near closed all the time. It will hunt. Any control valve will, whether it's a plumbing control valve or an HVAC control valve. It has to be sized right. And valves have minimum flow rates. So they have to see a certain amount of flow through the body of the valve where the sensing is to be able to operate properly. Why? If you have like laminar flow coming into a valve and the cold and the hot are just coming in really slow, they can be too laminar for the sensor, and the sensor will see hot, it'll see cold, it'll see hot, it'll see cold, and the valve will hunt. But if you have enough flow, then you get nice chaotic turbulent flow around where the sensor is located. The valve will be steady and it will control. So you always want to look at whether it's a thermostatic master mixing valve or a digital. You want to look at make sure that you know what the minimum flow requirement is. And usually, if you have a recirc system like this, you can just make sure that your recirc pump will deliver the minimum. So let's just, for example, let's see if we had, if we wanted to look at this 1-inch digital mixing valve here. As long as our circulator was pushing 3.1 GPM or better, that valve will be rock solid. It will control steady and it'll stay there and provide very consistent tempered water to the system. And that rule, by the way, holds true whether it's thermostatic or digital. Now, digital valves, which are more commercial, right, like in this, this schematic here, digital valves are more expensive, but they have a lot of benefits, especially in commercial applications. You can network them, you can have remote access, you can read and write set points to them, you can get data logging and alarms. They're gaining in popularity very quickly. And we highly recommend looking at digital master mixing valves whenever you're in commercial application. Also, valves have, in addition to a minimum, they have maximums or design flow. So no matter what brand you buy, look at their data and make sure that you use the valve that's the right size for the design flow or the CV that's recommended. If you, again, if you pick a valve too small, it's not going to be able to handle your heaviest times of demand. And if it's too big, then it will hunt a lot. So pay very close attention to the flow rates, the minimum, the design flow, and the maximum flow rates when you're sizing your valve. Now remember, if you're buying a master mixing valve that has a ball type as opposed to a globe valve, they have very high CVs. So it's not unusual to go down 2 pipe sizes to make a control valve properly sized. Okay, don't ever just put in the pipe size for a control valve, because usually that valve is going to be too big and it will try to control near closed all the time and you won't get consistent temperatures. So pay attention to the CVs. Try and get total hot water GPM demand from the building. If it's retrofit, that's hard. You just don't know, but at least try and estimate it. If you had a 50 room senior living center and you knew that each of the apartments might be using 2 or 3 GPM at the same time every day, then you can come up with an estimate of hot water that you need and try to do your best or get the GPM load or the demand from a designer. Okay, we talked about the design flow rate. So for example, this red box here, the design flow, this is the Caleffi product, and this is the design, this is the GPM at 7.5 PSID pressure drop across the valve, which is a really good pressure drop for a modulating ball valve, and that works for ours. Now the valve will handle up to what we call this maximum here, and that's we rate ours at 20 PSID. So the valve will deliver more than that, but that's going to be an unusual condition. The sweet spot for sizing is our design flow rates. Balancing. Let's talk about balancing. This is the big one. We really need to get balancing contractors to produce a balancing report. I hear every day, almost every day, that, oh yeah, right, good, you want it, but it just doesn't happen. A balancing report, they never see balancing reports. It's too bad, but it's near the end of the job. They're one of the last contractors on the job, and if it's behind schedule and they're over budget, sometimes the report doesn't get done. But there's a lot of references here that tell us if at all possible, we need to have that done. ASHRAE standard 188, for example. In the department that I work at, the most common complaint we get on this topic is that the system isn't balanced. We have the tenants, the occupants way out here on the east wing or something, they never have hot water. They turn their shower on and then they go make a piece of toast and get a cup of coffee and come back and then it's warm. That's a balancing problem, okay? That's what we hear a lot about. And balancing is not easy, but it can be done and it can be done right. Let's talk about balancing valves for a couple minutes. There are three types: manual, called also static balancing valves. These are all just an adjustable restriction in the line. That's all it is. They don't have any moving parts. They're pressure dependent. That means that the flow through them will change as the pressure changes. Once you set them, they're just a restriction in the line. Okay, they're kind of the traditional valve that's been around forever. Typically, they're lower cost to put in, but they're very labor intensive. And way too often we see pictures or have customers call in, contractors call in, and they find these wide open. They go into an existing building and, yeah, the valves were all wide open. Well, yeah, that's your problem. That's the problem. So they can work. They can work just fine if they're properly installed, properly tested. And if you look over here in the schematic, always locate balancing valves here in the return. Okay, here's the supply trunk. There's the supply that goes out to the fixtures, and this return right here, somewhere in this line, is where the balancing valves go before these pipes tee into the return trunk that goes back to the recirc pump. That way the balancing valve is controlling the flow for the set of fixtures where it's located in that group of fixtures in that riser. And you can use these with a constant speed pump. If you get everything set up, you get them all balanced properly. It's an iterative process. You have to go back and forth. Once you set one and you go set the next one and the next one, you have to come back and tweak the first one again. So like I said, it's very labor intensive, but it certainly can be done. The second valve, automatic, or what we call dynamic balancing valves. Think of these as a fixed GPM valve. They are a constant flow valve, and they're really, really cool how they work. Inside is a cartridge that has a spring in it. So as the fluid pushes against the face of this cartridge, it compresses the spring and pushes this cartridge in this direction to the right. And what that does is it will close and open the flow paths around the cartridge. So the fluid comes in here, goes around here, comes through this characterized opening, and then out. And it's designed such that that characteristic opening and the compression of the spring match up so that you get a constant GPM between a given differential pressure range. Like from 2 psi to 32 psi, this valve would stay at a constant GPM. So what you do is you order these based on that GPM. You could order a valve with a 1 GPM spring or a 2 GPM or 1.5 or 6 GPM. And what that means is the size of these openings right here will vary based on the GPM you want. So it's all calibrated to work together. They're not adjustable. If you order one and install it and you decide later, well, that's not the right GPM, you have to take it out and replace that cartridge. Some of these have a kind of a Y body, and you can just pull the cartridge out and put a new one in if you didn't install the right one in the first place. So they're inexpensive. They work great. For a designer, it's nice if he knows for sure, he or she knows for sure that they want a given GPM and a given circuit. They're a great solution. And you can use these with a constant speed pump as well. The third type is a thermostatic balancing valve, relatively new in the industry, but really gaining a lot of traction. These are my favorite, and I'll show you why. These valves modulate. So if you look at this graph in the lower left-hand corner, on the bottom on the x-axis here is temperature. So when the water coming into the valve is cool or cooler than the adjustment on this set point knob or the pre-calibrated cartridge, the valve opens. So they actually open and they have a changing CV. So as the valve opens, it has more capacity. As the valve closes, it has less capacity, and it's all based on temperature. This gold colored cartridge in here is a sealed wax element. It's very sensitive to temperature, and when it gets cool, it contracts to open this seat right here, and when it heats up, it will expand and extend to close down this seat. It doesn't fully close ever, because there has to be a little bit of flow going across this sensor for the valve to be able to react to the system. So you can see here in the graph, when it closes down, it will reach what's called a CV, a minimum CV, and it will stay there as the temperature goes up. So that's what's different about it. It actually modulates and changes GPM in this system. And no matter which brand you buy, they're all basically the same kind of thing. They use a similar sealed wax element that opens and closes the flow path for this seat. In this cross section, we happen to show one that has a check valve and an insertion temperature gauge. This is what that one looks like in a photograph. So it responds to changes in supply temperature and delivers the flow needed, whatever that flow is, to maintain temperature. And if you think about it, we're really interested in just temperature. That's all we want. We want hot water at these fixtures. We don't really care about differential pressure or GPM. We just want the temperature to be consistent. So that's why these are so nice, is they get right to the point. So they control its set point regardless of inlet temperature. Right, so if you have this one set, for example, at 130 degrees Fahrenheit, it will open and close to try to maintain 130. If the temperature drops, it'll open up, bringing more water from the supply trunk into this group of fixtures to try and get to 130. The same thing will happen way out here at the end. The water coming into this riser probably not going to be the same temperature as the water coming into this riser that's really close to the heat source, right? It's going to be less, but that doesn't matter because the valve will still control at 130 degrees Fahrenheit. So you just install these, an adjustable one, you just set the knob to, 120 or 125 or 115 or whatever you want, and you're done. Great for retrofit. Why? If you go into a building and you don't really know where all that piping is behind the walls, you don't know the heat loss of the system, you don't know the GPM, it doesn't matter. Just put these in, and as long as that riser or that secondary circuit has some hot water, the valve will try and maintain the temperature in that section of the piping. You don't really want to use or mix and match different types of balancing valves. I guess you can, but it would be more difficult to achieve a stable system, and I wouldn't want to be the maintenance guy who has to go around and service valves if some of them are thermal and some of them are manual that require a differential pressure tool. Try and stick with the same type of valve throughout the system. Make sure and check each balancing valve. I know that's a lot of labor. The commissioning contractors should do that, but we know that after they're gone, then whoever owns that building really should take ownership and make sure that everything is balanced. And I mentioned before, it's the last, but it's the most important step in commissioning. Okay, just a few more slides here, and then we have time for Q&A. We've been getting a lot of questions about how to do recirculation in high-rise buildings where there are PRVs. So here's a schematic that shows one solution. So let's look at this for a second. So we have our supply water coming in here. Here's a pressure reducing valve coming in to reduce from the street pressure down to the system. We're showing a tank here, as I mentioned too. This could be tankless or heat pump water heater, doesn't matter. We're showing a digital master mixing valve here, but the important thing is, look at the recirc loop. So it's running on the high pressure side of the PRVs in the building. Okay, the cold water goes through a set of PRVs to serve a particular zone. This could be a group, maybe 1 or 2 or 3 or 4 levels, or it could be 4 or 5 apartments, whatever. But we have PRVs here, and we're running a high pressure riser with PRVs to serve the zones. So this is one way to do it, right? Recirculate here. All the recirc is located on this side of the PRVs. So you could have a high pressure system. You could have booster pumps here too, and your recirc system is going to be piped the same way. So there might be some questions on this one, and we'll get to them as they come in. Another way to do it, now this is a different diagram, but I don't have a better one. The rule is never try to recirculate across a PRV. It will not work. You can't do it. You can't recirculate and then push water back into a high pressure system on the backside of a PRV. What you need to do is, okay, over here on the far right, this is our high pressure piping over here on the far right. What you can do is set up a PRV station, and that PRV station is going to serve all of your risers and your balancing valves and everything out here, all your fixtures. But you can put in a plate heat exchanger right here. Look at the piping before you go to the PRV, pull off your high pressure, run it through a plate heat exchanger, put a balancing valve in there, and then go back to your high pressure. So everything over here is in the high pressure system. So then on the other side of this plate heat exchanger, you're going to have your zone circulation pump, pumping that water through the plate heat exchanger and serving all of your risers or your secondary circuits here on the low pressure side of the PRV. Okay, that's another way to do it. I know this is expensive. Plate heat exchangers aren't cheap. You can see there's a lot of devices in here. You have air vents and thermal expansion tanks and balancing valves, but is one way to do it on the downstream side of a PRV station. That would be expensive if you had to do that on every third or fourth floor, but it's a great solution. We know it's proven, and we know that it works. All right, well that takes us, we've got about 7 minutes left here. We want to wrap up and tell you about our technical support team. These are the guys that work with me, the best in the business. They are licensed plumbers, professional plumbers, HVAC technicians. These guys are the best, and they do training for us both remotely and locally and hybrids. So there's our phone number that goes right to the group. So if you call that 6338 number, it goes right to these guys. If they're all on the phone, that call will roll up to me. So we try to answer your call live and help you as best we can. And there's our email. That's a really good email to have, techsupport.us@caleffi.com. Send your questions over to us. Our journal, our loved journal, the hydronics that we produce, we mentioned at the beginning, these two are relative to what I talked about today. So issue 21 for recirculation, that has all the calculations and the details about what I talked about today. And issue number 22 talks about the master mixing valves. And these two are very good. You know, they're free, right? You can sign up to get hard copies, or you can look at these. They're all available free in electronic format as well. Okay, Max, we came in under the line. We've got about 6 minutes. What sort of questions do we have?
We had a bunch of questions. So we answered some of them during the webinar, and some of them we'll follow up with after the fact. A couple that may help to go back a few slides. We go back to the one where you had the high-rise building before the one more.
This one?
Back, yeah, right there. So the question was same scenario, but let's say the water heater is at the top of the building in a penthouse mechanical room or something like that. Booster pumps at the bottom. Would you change anything major with this drawing?
No, if that's a top feed or a bottom feed, as long as you're recirculating on the high pressure side of the PRVs, you can basically do it's the same.
Okay.
Yep.
And then we
It's
had a question that you addressed with the kind of mix and match of balancing valves. So let's say you are the maintenance person who takes over a hospital and there's some mix of thermal and automatic and manual balancing valves.
okay.
What are you up to there? What would be your best foot forward to try and find a specific valve that works, or what would you do in that case?
You mean if you had different types?
Yeah, so let's say you inherit a building that's got all three of those valves or different technologies. What would be your best
I would,
option?
yeah, I would highly recommend putting in thermostatic balancing valves everywhere. They just solve a lot of problems, right? They'll do what they're made to do with what you have, right? If uh, they will try to control at the temperature no matter what's going on in the system. If they still can't deliver, then you have a bigger problem. Then it's not a balancing valve problem, right? If you have one riser that just, even if you put a thermostatic balancing valve in there and it still doesn't work, there's something else going on in there, like a cross connection or something more serious. But these are a real problem solver. I would recommend replacing everything with the thermostatic.
And you kind of mentioned it as well, but if you've got a mix of a static, like manual balancing valve that's set to a specific orifice, but then you either have automatics or thermals that are modulating, that manual balancing valve is going to be, what's the expression, like a broken watch is right twice a day. um, that
Yeah,
like
yeah. Well,
you'll never have that manual balancing. You won't be able to balance that correctly. You wouldn't know what to set that to anymore.
right. Manual balancing valves are pressure dependent. And we know that these systems are dynamic, right? Whenever you open a Roman tub valve, it's going to affect pressures in the system. It even will affect valves in other risers. So the only time these systems are static at all is at night when there's no water usage. But anytime during the day, if a fixture opens or if you have a modulating thermostatic balancing valve, that manual balancing valve isn't going to be right. Right? It's only right at a very specific set of conditions. So I think your broken watch is right twice a day is pretty good reference for that kind of thing.
We also got a couple additional answers for kind of the run out to fixtures. So we had um, Art put in some math that if you're talking about half-inch pipe for a 0.35 GPM fixture and you want to get hot water there in under 10 seconds, like that math is calculating out to 8 feet. We also had an answer from Wisconsin that inspectors are looking for 6 inches, which is a whole different. We actually had a Wisconsin kind of specific Legionella webinar last year that I'll look for that link while we're still in the call and put that into the chat. That's a best case scenario. That's more like they do it in Europe, where you actually recirc like as close to the fixture as possible. So you're actually recircing within. It's like the stub out is actually a U fitting that you recirc past. That's kind of the probably the absolute best way to do it. I'll say that's a completely different amount of pipe for that project, and we haven't really seen that um, type of system adopted yet. But it sounds like if that's
Yeah.
what they're enforcing in Wisconsin, you're gonna have to recirc like that. What we're showing is the laterals there. You'd have to recirc past those basically, which is a lot more pipe, but is a good practice to have the minimum amount of stagnant water potential and run out there.
Yeah. I think there's
Those
actually a thread on the ASPE forum today about that exact thing. So
Yeah, it's a hot topic. It's hard to know what the right number is. We had another answer was 16 ounces of water. So even to know like what the metric is, which is
Okay.
great. That would be nice to get just less than 2 cups of water to get hot water, but is different metric than feet or inches or whatever. There was another question, another comment about the recirc pump being less expensive energy wise than all the heat loss of the pipes for a recirc system. I wanted to put in the chat there that the last link I put in was the webinar we did with Gary Klein 4 years ago, and he goes into a case study there where he shows the amount of energy that was lost just with the heat loss of the recirc loop, and it was shocking. And I think that that's the case in a lot of situations, that an ECM pump is going to be like a light bulb compared to the amount of energy you're going to dissipate just between floors and things like that.
Exactly. Yeah, I mean, I think 25 to 40 watts is the range that I saw on these new pumps, and that literally is an LED light bulb, right? Um, in the grand scheme of things, it's nothing. So I would hope that the general practice going forward will lean towards just keep the water moving, just keep it moving, and everything will be a lot better off. You reduce the potential for stagnation and keep things moving.
We had another. We had a comment that balancing an open system is a tall task. So when should you do the balance? Like regardless of the balancing valve, do you want to do that pre-occupancy or post-occupancy?
Yeah, you can't balance a system when you have fixtures that are open. You have to do it and treat it like a closed system. Yeah.
And we
So when
definitely
you're commissioning the job, you need to make sure that no fixtures are running because you need to get the whole system balanced as if it were a closed system.
and we've had those tech support calls where people are looking to balance after a hotel is occupied or something like that. Um,
Yeah.
3 in the morning, maybe. Is that you're like the I don't
Well,
think
I
that
guess,
the plumbers or the balancing contractors ever want to hear that, but like best case scenario, you try and find a time of day that
yeah.
the potential for usage is lowest, but nobody wants to be balancing at 4 in the morning. But it's better than not balancing, attempting it, I guess.
Well, we hope that balancing is done before they get occupancy. That's what we hope.
And then we had another question about cold water recirc, and I know this is something that we hear about as far as like, let's say you have a hotel in Arizona or something where there's potential for the cold water lines through the attic to be kind of in that 95 to 115 degree Legionella growth range. Um, what are you seeing kind of with that trend, Kevin, as far as cold water recirc in addition to hot water recirc, and like where would you look next to know if that's something that should be part of scope?
I think it would only make sense in a very hot region and if there's a big fat budget for that job because and it can be done and it is done. It's not common. I haven't seen any. I've never been to a job that had that, but you could use a manual or an automatic balancing valve, but you'd have to use a thermostatic balancing valve that has a reverse acting cartridge so that it opens when it gets cold instead of closes. And there are those available, but that's still a technology that I haven't really had any experience with.
I think that kind of takes me through the additional questions that I had
Okay.
on my notepad here. I don't know if Bob, you have any other questions that stood out from, well, as I was talking there, if anything else came in from the crowd.
Yeah, there was a lot of really good questions. I think we've answered a lot of them, but the one that Rick had asked about the descaling function, Kevin, you know how long that takes? Max said something. I think it's different on different size valves. Does it go all the way around, or does it go halfway and back when it does the descale function on the Legio mix?
Our Legio mix valve will uh, will turn all the way clockwise and then turn all the way counterclockwise to both
Yeah,
ends. So no matter
that's
where it is in the cycle, it'll go all the way one way, which is 90 degrees total. So if it's in the middle, it'll go 45 degrees and then go all the way back to the other end and then come back to where it was.
yeah,
That's the anti-clog cycle.
that's what
And
I
the
thought. You don't know how
actuator,
long it takes.
I mean, our actuator is, I think it's a 50-second actuator. So you're looking at least at least 100 seconds. It might be closer to 200 seconds.
Okay.
So yeah, it takes a couple minutes.
Let's see what else.
By the way, everybody, we'll answer if we have a question that we don't get to, we will look those over, and Bob or Max or myself will send you an email response to your questions.
Yeah, they're still rolling in. I'm trying to catch up with them here. I'm not a very fast typer, so I'm a little behind. But yeah, the ones that we haven't answered, Max or I didn't answer in the chat here, we'll get back to. We don't let anybody hanging, so it might take a day or two for us to get through all these, but we'll definitely get back to you.
Yeah. Well, I want to respect everybody's time. I mean, I'm okay to go a little bit over, but I don't want to go too far over, just to make sure we respect everybody's time. But I'll hang in there for a little bit if we have
There was one
more questions.
question about the minimum flow rate through a valve, through a thermosetter that could maybe cause overheating. But I mean, the thermosetter type of valve needs to have some movement through it so the sensor can respond. So I guess on a short loop, there is a potential for it to overshoot a little bit on temperature. I don't know how you would design that out of a valve.
Yeah, I don't know that there's a good answer for that one.
Yeah.
It'll
And a
close
manual
down
valve
to,
would do
yeah,
the same thing on a manual valve, probably worse because
worse. Yeah,
the
worse. Yeah,
thermoset at least can close down to the
yeah.
lowest point. So
And that's where you want to have control over that back at the source at your master mixing valve, right? You want to be able to close that off so you don't get overheating.
yep.
And I think that I don't remember if you covered this at the beginning. Any situation where you were doing thermal disinfection, you'd want point of use mixing as well.
Yeah,
So
yeah. And anything having to do with thermal disinfection or shock treatment in the recirc loop, that's a whole different webinar that we've done, and it's a meeting that's another hour meeting. So
we got a couple material questions that you do want to use a balancing valve that is for potable water for this scenario, even though there are
yeah,
types of balancing valves that are not that are intended for hydronic systems that may look the same. You definitely want something that's
yeah,
suitable for your
very important.
authority, having jurisdiction to have the right um, low lead certification or NSF
Yep,
listing.
that's NSF 372. You have to have NSF 372. Not necessarily NSF 61. That's for drinking water, but uh, and this is a hot water system, so not exactly drinking water, but that's another thing that gets discussed. But it has to have NSF 372. That's the low lead law.
Yeah, that's another webinar because when that comes
Yeah,
out up during
yeah,
training that we do outside of Coffee with Caleffi,
right.
the water heater doesn't carry an NSF 61 um,
Yeah,
listing. So, like, should you ever drink hot water is kind of a funny question to ask. People, have opinions about cooking with hot water and things like that as well.
yeah.
Um, okay, let's see. I think some of these we might have to spin off to answer offline. Do you see anything else
Okay.
that we
Yeah, we'll
should
do
snag?
that. We'll go through those, and we'll get back to you. Everybody, we'll get back to it with a reply. And really, thanks for hanging in there with us today and being there for us. You know how to get a hold of us. Here's our information, and we'll let you go. We'll see you next month.
Thanks, Kevin.
Yep. Thanks, Bob. Thanks, Max.
Thanks, everybody.